Hello, and welcome to the webinar, Key Trends Driving the Need for More Semiconductor System Level Test. Your presenters are Anil Bala and Karthik Raghunathan of Astronics Test Systems, and I'm your moderator, Rick Nelson, Executive Editor of Evaluation and Engineering. Before we begin, I'd like to remind you that you can ask questions at any time during the presentation. Our presenters will answer them at the end. We will also be asking you some polling questions during the presentation and provide the results in real time. We encourage you to respond. And now I'll turn the program over to Anil.
Thank you very much, Rick. I first of all would like to thank Evaluation Engineering for their help in sponsoring this webinar. We're very excited to be part of the system level test trend that is going out throughout the industry, and we hope that you'll enjoy the webinar. As Rick mentioned, we would love this to be as interactive as possible. So if you have any questions, please submit them and we'll try to integrate them through the presentation. Astronics has been in the system level test business since the mid-1990s. And over the last couple of years, we've been very excited by the amount of industry discussion going on around system level test. We've seen activities going on not only at ITC and Semicon West, but other trade shows. And in general, it seems like there's a lot of interest in system-level test, driven by the need for advanced packaging and other things that we'll talk about today. So we think this is a great opportunity for us to share some of the insights we have and hopefully get your insights as well. We're going to target this webinar for those that are not too familiar with system-level test. So we'll start with a few basic descriptions and definitions, and then we'll get into more of the technical presentation to help those that are more familiar with system-level test proceed. I'd like to first of all introduce myself. My name is Anil Bala. I am the Senior Marketing Manager for Astronics Test Systems. I've been involved with the AT industry for a number of years, and very excited to be part of the system-level test trend here at Astronics.
My name is Karthik Raghunathan, and I'm the Director of Engineering for Commercial and System-Level Test Equipment. I've architected several system-level test solutions in coordination with my hardware, software, and mechanical engineering team. Prior to this, I used to run a system-level test group at a large semiconductor company. So I've been on both sides of the SLT business, which is architecting SLT test systems, as well as running SLT test systems in high volume across millions of devices.
We decided to break the webinar today in these 4 topics. We'd like to first of all start with an overview of what system-level test is and how it's being done today. Then we'll dig deeper into some of the key business and technical trends that we see driving additional requirements for system-level test. And we'll wrap up the conversation with a discussion around some key challenges and opportunities that we see in the industry. Before we begin, we'd like to start with a couple polling questions. And I'll go ahead and launch the polling questions right now. And Rick, if you can go ahead and help us go through them, that'd be great.
Sure. First, we'd like to hear what industry you serve. Consumer electronics, smartphone, tablets, streaming TV, automotive, data centers, wearables or Internet of Things, or something else entirely. So take a minute and check off the appropriate box for you, and then we'll take a look at the results.
Okay, it looks like the results are still coming in, so we'll keep it open for a couple more seconds. Okay, we'll go ahead and close the poll right now. Let's see if we can share the results. Okay, here are the results from the poll. Go ahead.
Mostly looks like consumer electronics is well represented here, and also none of the above.
Yeah, it's interesting to me. I think for the consumer electronics, there definitely has been a lot of discussion around getting into high volume and yield and quality. I think on the automotive section, we see automotive industry, we see a lot of interest in the quality, and so I think that definitely makes a lot of sense. And I think data centers have traditionally been very active in system level tests, so that's pretty typical as well. Okay, let's go ahead and do our second polling question before we go on to the presentation.
Okay, tell us what platform your company uses today for system level test. The choices here are ATE equipment, where SLT is added in some fashion. Maybe you use an internally developed SLT or a commercial SLT tester with multi-sites, massively parallel SLT with 100 or more sites, or perhaps you don't do any SLT at all today. So take a minute to check off the appropriate box, and then we'll take a look at the results.
Okay, we'll keep it open for another couple seconds. Okay, let's go ahead and close the survey and take a look at the results.
Okay, internally developed SLT is slightly ahead of ATE equipment, and also a substantial number of people are not doing SLT yet.
So Karthik, what do these results mean to you here?
I think these results are fairly interesting in that I think a lot of companies do start with internally developed SLT and try to start adding a lot of equipment to the ATE, which is done by default at final test. And yes, we do have a significant percentage of industries where SLT is not the norm today. But given the interest in the seminar, I'm assuming there's some interest in moving towards SLT, or at least considering it as part of an alternative.
I think the other thing we see going on in the industry is the people that are doing their internal SLT have really had no other choice before, and we'll talk about this in the webinar. So this is now the first opportunity that we see commercially viable solutions available, and we see that as a trend along with the need to do more system level tests. So that'll be part of our conversation during this webinar. Okay, let's go ahead and go to the next slide. So just a background to make sure we're all thinking about the same things. First of all, in this webinar, when we talk about system level test, we really are focusing on semiconductor system level test. System level test as a generic term can mean many things to many different people. At ITC, for example, there is a discussion that even helicopters can use system level test. And so we want to be quite clear. In this conversation, we're talking about component, and we'll also refer to it as semiconductor or DUTS, device under test. It all means basically the same type of things. What we're essentially trying to do is to take application-specific tests that are performed on that device under test. We put that device in a socket, and we help guarantee that that device will work among its targeted specs. But more importantly, we're trying to test that the performance goal, when it's ultimately used in the final system, is tested properly. So once again, we're trying to look for that device is not only operating as it should, but it's operating effectively with the other devices in the system, as well as all the software that needs to be in place in the final system. So again, as we are talking about system level tests, including both system hardware and software, by hardware, we're talking about DUTs, sockets, application boards, power supplies, etc. On the software, we have to remember all the different elements of the software that are included, everywhere from firmware to the device drivers, operating systems, and even applications. So system level test is trying to get as close as you can to the final end user experience to validate that the product is working correctly. One of the key notions that is arriving today in the industry is two different perspectives of system level test. One is called the component perspective, and the other is the system perspective. And depending on your point of view, it really dictates how much system level test you are doing today or might need to do in the future. If you're coming from a component perspective, you are basically trying to test whether your device is meeting. And typically that's driven by doing that test on an ATE type of tester or some other tester where you're trying to make sure that that device is working properly. If you're coming from the system perspective, what you're really trying to do is test that that product is working as a system, along with the other hardware and software that's intended for the final application. Traditionally, we have found that the system perspective is driven by mostly quality engineers who are measured a lot of times on yield. And on the component perspective, it's traditionally test engineers who are responsible and accountable for making sure that the device operates as it's intended to. But one change we're seeing in the industry now is test engineers are becoming more and more accustomed to being measured on yield and quality. So I've seen a number of customers where their metrics are changing from a test perspective, where they now have to think about how quality and how yield improvement can be improved quarter over quarter. And so many of those component perspective people are turning into system perspective people. And we see that becoming more and more important as new packaging and new nodes, lower nodes become prevalent. But keep that in mind as we go through this conversation. The other thing that's important to note is that we view system level test as a custom solution, if you will. So we do believe that you can purchase commercial viable equipment, but in the end, you have to customize those components around your particular application. So depending on your thirst and the familiarity of doing that customization can also dictate how much system level test you will be familiar and comfortable to do. This is how we got here in terms of system level test. And I think, as you all know, the first version of testing was really focused around functional test and testing the patterns and making sure the device was getting the right patterns. And for many, many years, functional test was able to keep up with Moore's law. What we saw in the many years following that is that structural test became important, and it was added as another vehicle to get full fault coverage for your device. And the combination of functional and structural test, again, for many years, did a good job of keeping up with Moore's law. What we're now finding is that functional test and structural test by itself is not enough to cover a device 100%. And we're seeing now the emergence of another vehicle or another tool that customers can use in order to get 100% test coverage. And it's really important that system level test is seen as a vehicle. It doesn't necessarily replace structural or functional test. I think we see this as things that go hand in hand. And there's definitely a lot of opportunity in the future to try and figure out how to merge all three test strategies into a complete test portfolio. How much system level test? It's really dependent on a number of different things, and let's go through this in some level of detail. The perspective you have is, I think, very, very important. Are you coming in from the component perspective as we described, which might dictate less system level test, or are you coming in from a system perspective, which means you really want to test that system as that device under test as part of a system, and you're really looking at yield or quality improvement. You know, how much hardware and software interaction issues you have. If you have a lot of hardware and software interaction issues, what we find is that testing a device in the traditional ATE isn't sufficient, and we're finding a lot of people are moving towards system level tests to identify those hardware and software interaction issues. They become very, very difficult to find in a traditional ATE environment. Karthik will go through a couple examples in a few minutes about that particular topic. Volume, market segment, and product lifetime become very important as well. If you're in a very high volume market, you might be looking for a commercial viable solution to take into production test. If on the other hand, you're looking at a very low volume product but need to do some system level test, you might be driven towards a custom type solution environment which might be suitable for your needs. The market segment becomes important. If you're in a market such as automotive or medical, where quality or lives depend on the ability of your product to work correctly, you might be driven to do more system level tests in the future. Thermal requirements. What we find is that there are many applications where you have to test your device under a wide range of temperature. And we find that doing that in an ATE environment is one methodology, but we're finding a lot of interest in doing that in system level test. And the other area we see a lot of industry discussion is looking at burn-in and system level test and how those can work together in the future. So the amount of thermal requirements you have in your application can drive you to do more system level tests. Cost of test escapes. This is really the industry well-known thought that you want to catch your defects early. And what system level tests have a tool for your highest volume parts where you're able to validate and test and find parts that are failing and find them earlier in the process. The last thing you want to do is to basically ship parts into a final product, the cost of those returns become very, very expensive if you're in a consumer type application. And if you're in other markets, they can also become very expensive either from a quality perspective or even a liability perspective. So the cost of your test escapes becomes very important. And as I mentioned before, end market requirements can be very critical. Well, we're seeing some constraints or some challenges to the industry from the medical space, for example, as you see people going into more remote patient monitoring and continuous patient monitoring of devices, that quality becomes really important. So we see that continuing in the future as well. The next part of the conversation is really how system level test is done today. And this is not a complete set of all the different variations, but I think it should give you a pretty good overview of what we see. On the left side, you'll see a order of magnitude in terms of cost per DUT, or cost per device. And on the bottom axis, you see volume. So if you start from the far left here, you see that, as we learned in our poll, that today there are many people that do system level test on what we call ATE. And traditionally this is done on load boards where you add load board circuitry, low volume applications, qualifications, that can also be sufficient. It does require you to have enough space on the load board, and that you also have to be concerned about the ATE latency, which Karthik will talk about in a few minutes. But that can be sufficient for many different applications. We do see people doing a system level test on ATE in qualification, so that is an option that we see people doing in the industry today. The middle category here, the system level test on custom hardware, I think that was the highest scored part of our poll. There are many early adopters of system level tests that are doing products that are typically low volume, that require very unique custom hardware, in many cases custom software, and in some cases very close interaction between the design teams and the test or quality teams to develop a test. And traditionally those people and companies have developed and built up special teams, anywhere from 2 to 10 people perhaps, and those teams tend to be combinations of hardware people and software people that are really focused on developing these system level test perspectives. That can be very successful depending on your situation. It does require long-term support, not only the software requirements, but also the programs and the hardware. And so we see that people are looking, as they go into higher volume system level tests, to try to go to commercial solutions if those are available. The third category is what we call low parallel SLT. This can be anywhere from 8 sites to 16 sites to 32 sites. These are basically commercially available solutions. Can be suited again if you have a very high mix type environment. The challenge is that when you go to very high volume type productions, you basically have to multiply those test cells, which over time can require more floor space and operators to adhere, but that has traditionally been another approach. The final and last systems that we see doing system level tests is what we call massively parallel SLT. Those can go up to 5,000 units per hour, and we see systems now. Astronics has one that goes up to 400 sites, almost 400 sites per DUT. And so we see for some of the consumer or higher volume products, that becomes a very important part of the production test. And as people go into more and more production tests of system level test, we see this as a very viable approach. So anyway, that's a quick summary, and we can talk more about that in this presentation or offline if you have any questions. But traditionally, that's kind of where we see the market going. So I guess the last comment I'd make on this is that, you know, each one of these categories is trying to move in different directions. We see the system level test people trying to get into more commercial building blocks if they are available. We see some of the massively parallel systems out there going into lower parallel type applications, and on the next slide we give an example of that. So depending on the test time you have, if you're looking at test time in minutes or seconds or hours, you might be looking for a certain configuration. If you're going into higher volume type products, then you might want to take that building block and move it into a different configuration. So this is an example of a system that you can start with a building block of 1 site. You can then move to an 18-site single slot tester, and eventually move into things like manually using a chamber to put boards in and out, or get an automated elevator if that's something that you're interested in, and eventually moving to a more massively parallel solution. So I think what you see here in the industry is many different approaches, and I think we'll continue to see that evolve over time. very similar to the AT industry, where there was a very early interest in doing tests in certain niche applications. Over time, the industry matured where commercial solutions became available and became more cost effective. Several years that to continue being the case in this area as well. Okay, before we go on to the next section, let's take another poll and get some feedback from the team. So Rick, if you could help us with this poll.
Yes, we'd like to know what your cost of test is with SLT if you're currently using it. Less than 10 cents per device, 11 cents to $1, greater than $1, or perhaps you're doing SLT but are not sure of the cost, or perhaps you're not doing it at all. So take a couple minutes to check the appropriate category there, and then we'll take a look at the results.
Okay, looks like response. Give it another couple seconds. Okay, let's go ahead and close the poll and share the results.
Okay, a lot of people don't know exactly what they're spending on the SLT insertion. Otherwise, the people who have tracked it, it's less than 10 cents or more than $1.
Yeah, it's very typical for, go ahead, Rick, sorry.
Yeah, I was just going to ask, how does that comport with your understanding of the market here?
Actually, this isn't very surprising because I think a lot of these SLT solutions seem to be internally developed solutions. So if they're internally developed solutions, there isn't a fixed cost associated with the NRE for capital equipment. So it isn't surprising that a lot of people seem to be doing SLT but aren't exactly sure of the exact implications of test costs. I'm assuming that for those who know the exact test costs, they have moved on from internal equipment to either doing SLT on the ATE or on a parallel system or using some commercial equipment, because then it becomes easier to estimate it as a percentage of cost.
Mm-hmm.
Okay, we have one more polling question before we continue the presentation. Let me go ahead and launch it now.
Okay, what is your target cost of test to adopt SLT for production? And same categories, less than 10 cents, 11 cents to $1, greater than $1, or not sure, or not currently doing SLT.
All right, looks like the poll is coming up right now.
Oh, okay, it looks like I
It was me. No problem.
got ahead of it there, but the slides have caught up. So yeah, just tell us what your target cost of test is to adopt SLT.
Okay, another few seconds here. Okay, we'll go ahead and close the poll here. And let's take a look at the results.
Okay, so less than 10 cents per device for the most part, for those who have tracked it.
So it's interesting that with the same number of respondents, that it's unclear what, which is not, it's not unusual as Karthik described, yet I think there's an industry-wide idea that the cost when you go into production has to be less than 10%. So we have 45% of the people that say they know the target but may not know the current cost, which I think is very typical, as Karthik mentioned, for people doing a lot of internal SLT where they have targets in place, but it becomes very difficult to measure and quantify that. Okay, the next part of the presentation will be to talk about some of the key business and technical trends that are driving system-level tests. So I'll turn the mic over to Karthik.
All right, so I think Anil's focused a little bit on the business drivers for SLT at this point in time, and I'll focus a little more on the technical drivers that are driving the adoption of SLT. One of the biggest technical drivers we see is node shrink and the increasing need for at-speed coverage. Another key technical driver that we will delve into details is the reality of concurrent testing and the real-world scenarios where multiple things are happening on the end product at the same time, both in the hardware domain as well as software domain. The stack of guard bands as well as yield overkill caused by the stack of guard bands is another driver for SLT. The increasing explosion of PVT corners combined with voltage and frequency scaling jointly acts as a driver for SLT. Packaging, both 2.5 and 3D, and the increasing complexity of IP getting integrated into these packages also is a key driver for SLT. So moving on to addressing the topic of node shrink. Moore's law has been around for quite some time, and the transistor count more or less appears to double every technology node. For instance, the 22 nanometer technology node, a typical SoC had about 2.5 billion transistors, and if 0.5% of these transistors were not covered with structural or static ATPG patterns, we had 12.5 million transistors that were untested for stuck-at faults. But about 375 million transistors were not tested with at-speed or transition delay fault patterns, right? Because typically for at-speed patterns, the coverage we polled in industry seems to be hovering around the 80 to 85% mark. Now, if we move over to 5 nanometer, where the transistor count is projected to be around 40 billion transistors, then 200 million transistors aren't getting tested for stuck-at faults. But 6 billion transistors, which is a mind-boggling amount, 6 billion transistors aren't tested at speed. So this is increasingly driving a high number of test escapes and DPPM at the end customer, driving the need for system-level tests. Another key driver for SLT is the fact that the real-world scenario is extremely complex. Let's consider a mobile DUT where a video game is playing, an app is being downloaded, Skype is running in the background, a timer is running, and then an audio call comes in. We're just assuming that when the audio call comes in, all of these apps and all of these other 4 things just move seamlessly to the background, and the minute the audio call ends, all of these background apps recover very, very gracefully. If the end customer reports a problem where, let's say, the minute a mobile audio call ends, Skype crashes, and such a scenario has to be replicated on the ATE, generating such a vector would often take weeks to actually converge. And once the pattern converges, ensuring that it can be actually deployed on an ATE without any significant overkill of yield often takes months. Whereas at the system level, to be able to generate such a scenario where a video game, an app, a Skype, and a timer are running, and an incoming audio call comes in, it's usually a matter of about 4 to 5 minutes to be able to do this scenario in a real-world test case. And that's the beauty of system-level tests, because it allows the exact end scenario to be replayed. With a different kind of automotive DUT, the same scenario holds true. Let's consider a scenario where a navigation system is running, a satellite radio is playing, kids are streaming video on a Wi-Fi, a Bluetooth-paired phone call comes in, and then, believe it or not, a car comes swerving in the lane, which takes priority, and then the car swerves out. So the kids in the car expect the streaming video to play almost seamlessly as if the car incident had never happened. So this is another scenario where generating a production ATE vector for this situation often takes months, especially if you've got to ensure that there's no significant yield overkill, whereas generating an SLT test scenario for this is often of the order of minutes. On a slightly different note, we've often seen dynamic voltage and frequency scaling as well as guard bands added to ATE tests, right? So in terms of guard bands, the guard band is the margin that's added to an ATE test to compensate for the worst case difference between the ATE frequency or the ATE Vmin and the system frequency or the system Vmin, right? For this particular example, we're going to assume a 100 millivolt guard band. For all practical purposes, it could also be a 100 megahertz guard band. Now, as the VDD starts dropping across different technology nodes, the guard band, more or less, from our polling of customers, seems to stay flat at 100 megahertz or 100 millivolts. So in the 90 nanometer mode, when the VDD was 1.4 volts, a 100 millivolt guard band was about 7% of the VDD, but as a percentage of the headroom, it was around 11% of the available CMOS headroom. Switching over to the 10 nanometer technology node, a 0.7 volt VDD is about 14% of the 100 millivolt guard band. The 100 millivolt guard band now is 14% of the VDD, and it's 33% of the available headroom. So as this available headroom keeps shrinking, it leaves almost no room for process variation. And the process variation of 3 sigma means that if you've got to retain a 100 millivolt guard band, you've got to start throwing away good parts. So customers are often stuck with two choices and pick the worst or the better of these two choices. The first one is throw away good parts to ensure high quality, or the second one is to allow a few test escapes to go through so as to have a higher yield. Now what SLT does is you don't need to add a guard band for system to ATE delta at this point in time for SLT testing. And because you don't have to add that delta, SLT helps recover a whole segment of good devices that might have otherwise failed due to adding a guard band for ATE testing. We've seen a lot of customers change their frequency either statically or dynamically in association with the mode that the device operates in. For instance, if the device has a sleep mode, it operates at a lower voltage and at a lower frequency. If it's a nominal mode running, let's say, a few background applications, it's running at an intermediate frequency and an intermediate voltage. And if it's running, let's say, a high-end graphics or a video game in concurrency with an audio phone call or something of that sort, then it's running in turbo mode. And over time, even within these modes, there have been sub-modes. There's been super turbo, nominal turbo, and sub-turbo modes, and nominal modes, and super nominal modes. And the same thing goes with sleep, where you've got from deep sleep to hibernate to almost closer to waking up. Got a whole host of modes. And not only has this explosion continued in terms of increasing number of voltage and frequency combinations, the number of voltage domains has also exploded across devices. Gone are the days where an SoC had 2 voltage supplies, one for the core and one for the I/O. There are at least about 18 different voltage supplies feeding the memory, the processor, the graphics, engines all separately. Each of the I/Os happens to often be on a different domain. And when vectors have to be generated and run on the ATE, let's assume for a second that every vector can be simulated in every frequency and voltage combination. But even if you were able to successfully simulate all these vectors, there just simply isn't enough test time to be able to run all of these combinations of patterns on the ATE. What SLT does, it natively allows you to use different modes similar to how an end user would use it. For example, you could boot in nominal mode, which seems fairly typical for a large number of customers, run multimedia in turbo mode, and then when the device moves over to sleep, you go into sleep mode as a natural function of SLT. Without SLT, it's difficult and it's not almost impossible to be able to test all these relevant dynamic frequency voltage scaling as well as PVD corners. As we moved into the FinFET era, 3D geometries are driving new failure modes. For instance, earlier at the poly level or the gate level, we'd see a bidimensional failure where you see poly shorts or poly opens. But now we have a third category of fails, which are small fin cracks. And these small fin cracks are now extremely difficult to detect using conventional methods. Weir-voids due to redundant piers are another classic example that are often very difficult to detect. IPs from different vendors get combined to the same package. For instance, you get memory IP from a memory IP vendor and a processor IP from a different vendor. There's 100% disk coverage for the memory. There's 100% coverage coming in from patterns generated by the processor IP person. But when the two are combined together, there are almost no patterns that exercise the processor in coordination with the memory. And adding 200% IP covered blocks together doesn't ensure that the combination is tested 100%. System level test can actually screen for this mechanism because natively system level test will run a host of packets bursting between the processor and the memory. High-speed and bidirectional interfaces often have read-write turnaround times that are typically higher than the latency of an ATE. LPDDR, PCI Express, USB 3.0, these are all examples of scenarios where the latency of the ATE often is significantly higher than the speed of these interfaces. So these again get natively tested in SLT because LPDDR, PCI Express, and USB 3.0 and similar interfaces are exercised directly during the SLT test.
So a couple of observations coming again from some of the customer discussions and industry discussions. On the bullet around IP from different vendors, we see this happening a lot in some of the advanced packaging like SIP or modules, where customers are having to get IP from different vendors, and they don't have control over the yield or information. So I think as we all collectively see more SIP packaging become popular or modules, this second bullet here becomes really important. Is that something you're seeing as well, Karthik?
Certainly, and often these different, due to confidentiality reasons, these different companies often don't end up talking to each other either. So there is the memory vendor is often completely disconnected from the processor vendor, and they're relying on the technology company and the semiconductor customer to tie all of these pieces in, and that's why it's getting increasingly complex.
And I think on the last bullet, as we mentioned earlier, people are doing system level tests to some level on an HE system using the load board. So as people get more concerned about the latency of the HE systems, that may drive them to do more system level test, or perhaps when they go into higher level production, sometimes scaling that approach needs a different type of solution, which is where the commercially viable system level test platforms become important.
Certainly, and one of the things that we've noticed is everyone is extremely comfortable with the concept of designing a load board for an ATE system. In the system level test market, that notion is just about beginning to occur. Traditionally, what most companies have done is taken their traditional apps or debug board platform and use that as their SLT vehicle for production. We're now starting to see customers move towards an ATE style approach where they have an SLT system and then they tailor a board that is designed for production in accordance with that SLT test system.
So a question just came up. Let me just see if we can talk through it a little bit. Is regarding the FinFET cracks, and from your experience, how are those seen in terms of the test equipment? So the question is, what is the fail signature of a fin crack, and is that something that system level test can help?
Certainly. So in terms of fin crack, a minor crack in the fin it probably will not result in a classic stuck-at failure. However, it will degrade the speed of the device, however so minorly, in certain scenarios. So if it degrades the speed, let's say on a critical block that is between, let's say, the processor and the DDR, for instance, during a system-level test scenario where the processor is bursting packet after packet into the DDR subsystem, at the system level, you will see a degradation in that speed. And that's how you notice that this physical defect has manifested itself as a system-level failure. And another example is, let's say this happens in a PLL block. If it happens to be in a PLL block where there's a minor crack on the fin, this would end up increasing the wait time or the lock time of a PLL by a minor amount. And if it increases the wait time by a minor amount, that statistical variation may or may not have been accounted for when the PLL lock time or wait time settings were established for that device. So if that PLL fails to lock and there's a slightly higher jitter during initialization, the part may actually fail to boot.
Okay, so thank you for the question, and if anyone else has any other questions, please send them in. So thank you for going through the business and technical trends. Let's ask a couple poll questions here. So Rick, if you could help us walk through them, that'd be great.
Sure. So we'd like to know what device under test you were considering for system level test. A device only, such as a processor, a memory chip, or a PMIC, an embedded system module, a system in package, some other type of device, or perhaps you're not using SLT at this time. So take a few minutes and answer, and we'll present the results shortly.
Okay, we'll keep the poll open for another few seconds. Okay, it looks like the responsive has basically stopped here. Let's look at the results.
Device only is coming out on top with system in package second. Is that what you're seeing, Anil, from your customers?
Yeah, I think this is pretty typical for what we see. The device-only category here is I think includes a lot of the early adopters for system-level test. And as Karthik just mentioned, the system in package or SIP devices are becoming a new type of device for the industry. Those devices are starting to really explode, if you will, in the market. And there's a number of reasons why system-level test can really help and get full fault coverage. Okay, I think we'll be ready for our final poll.
Okay, and what is your biggest driver for system-level test? Device complexity, insufficient fault models, catching software-hardware interaction problems, pressure for higher quality, or other? So take a few minutes to check the right category there, and then we'll present the results.
Okay, looks like all the responses have come in. Let's take a look at the results.
Device complexity seems to be the top category with 42%, and no one is concerned about insufficient fault models, it seems.
So Karthik, is this consistent with what you would have expected from the audience?
I believe so. So in terms of hardware fault, when we talk about fault models, the question's often been in terms of hardware fault models, and which include structural test fault models and cell-aware test fault models and BIST and so on. I'm not sure if similar fault models are being applied to the software side of being able to capture failures. So it would be interesting to see how these results would split up if we actually did a category which said software test coverage.
Great. Thank you, Karthik, and thank you, Rick. Okay, to just take a step back here and do a quick review of what we have covered. I think there are a number of business and technical drivers that we think are enabling more system-level tests. On the left side, you see some of the higher-level concerns that we see from customers and also throughout the industry. Definitely the drive to higher yield and higher quality becomes very important. New packaging technologies, SIPs and modules, for example, are driving additional requirements for system-level test. Time to market and time to value ramps are continuing to be fast, but it's very difficult to keep up with that fast pace writing patterns alone. So the combination of writing patterns where you can, but also then adding system-level test as a way to get 100% fault coverage is becoming more and more important. And the final category of things that we continue to hear is, people's lives depending on the products that we collectively are all making, whether it's for medical, automotive, and even consumer products now are becoming more important that they work, and we now see that people's lives really do depend on our ability to produce quality products. In the bubble here, you see some of the challenges. There's always a teeter-totter, if you will, a combination of things that drive more system-level tests from the technical perspective. Karthik mentioned some of the PPT corners, mission mode things that drive more system-level tests. On the other side, the cost of system-level tests becomes a pretty barrier in many cases to do it. So what we expect to see going forward is the industry to continue to look to commercial solutions to help lower the cost of system-level tests. And given that many of us don't have an accurate way of looking at our current cost of system-level test, some ways to maybe quantify what we spend today on system-level tests could be also important. Some of the challenges that we see going forward, as I mentioned earlier, we do not see that there's one-size-fits-all system-level test across all applications. We do view that applications are different and there will be customization required to have the right products, the right hardware-software interactions to be tested as a system. So that becomes a challenge. Over time, we do see these commercial solution type approaches or building blocks, as we describe it, to help lower the cost of test and make system-level tests more prevalent. The next three kind of are being addressed with these massively parallel system-level testers. Correlation concerns between AT and system-level test. How do you add a system-level test insertion, and how does that work with ATE? That's a challenge and opportunity for us collectively to look at in terms of our test flow. The cost per device to add system-level test. Typically after a wafer probe and functional test, that cost becomes a very critical element, along with the throughput of today's current SLT testers and the large form factor. And what we mean by large form factor is trying to duplicate many test cells if you go into high volume production. That sometimes can add costs. The last three are currently being addressed by massively parallel SLT testers, and so if you're looking for an opportunity to go into high volume, those can be a value added to your flow. The ability to diagnose the root cause of system-level test failures. System-level test failures are very different than the traditional failures you'll see in SLT. If a device screen doesn't operate or it hangs up, that's a very difficult thing to dictate or find in a traditional environment. What we see is that going forward, that the addition of software engineers and software expertise, along with the traditional hardware people, becomes really critical. It's not really prevalent yet, so it becomes something I think we see over time, but I think it will become an important challenge to be resolved over the next few years. And finally, the fault coverage metrics are still early stages. Right now, we still rely on hardware and software engineers to diagnose the fault coverage and validate, for example, how much system-level test coverage is in place. And over time, we think there could be some tools available, but they don't exist consistently in the industry today. Finally, some opportunities going forward for system-level test. We see a number of opportunities, definitely common approaches to building blocks for system-level tests, as we've discussed. Ecosystem of standard tools and equipment. So I think anytime we look at adding an insertion or modifying an insertion, that requires an opportunity to figure out how the different tools work together. There's a lot of discussions going on in the industry. SEMI has a couple of task forces in terms of standard data formats that are ongoing. There's a number of other activities going on, but I think that is an opportunity for the industry. Data analytics is another big opportunity. I think we're all anxiously trying to figure out what to do with all the data that comes collectively from system-level testers as well as functional testers and wafer sort machines. So many people are building their own teams together to start looking at this data, but that continues to be, I think, an opportunity for all of us going forward. Quick summary here, as we mentioned, traditionally test has really been focused on finding hardware defects, but what we're seeing with us collectively going forward is it's now becoming more and more important to not understand how the device works by itself, but really more importantly how that works inside its final product, which includes hardware and software. Second bullet here, system-level test requires the optimal performance of the integrated system, and it's really being driven by a number of business and technical drivers that we discussed today. And finally, lowering the cost of system-level test is really an enabler going forward to do more system-level test. You know, just because the business and drivers and technical drivers are encouraging us all to do more system-level test, until we can figure out how to afford it, it becomes an opportunity. But there definitely are some exciting developments commercially being available. We have some portfolio products on our side that we think will help in lowering cost of test, and we're very excited about them. If you have an interest in any follow-up information, we do have a white paper that we'd like you to download from our website. We have the link here, and we also can include a link to it in the follow-up email that happens afterwards. So we think this is a very cool topic, and we look forward to engaging with all of you in the future.
Okay, thanks to Anil and Karthik for that informative presentation. And now I'd like to remind audience members that you can still submit questions. And here's a question right now that I think, Anil, you just sort of touched on. What standard building blocks are available to assist in constructing a custom SLT solution?
So from our perspective, you know, it starts with, you know, having a way to take your system level test approach and leverage some commercial components. So those can be software. You know, leveraging a test executive that spans different applications is definitely one component. We see the building blocks of, for example, the single slot tester approach, which is an 18-site type tester, which then can scale into higher volume type products with multiple slots in the chamber, and eventually a fully automated solution as another opportunity. But these standard building blocks, if you will, should all be linked together so they allow you to leverage your investment as you go into different applications and different levels of volume.
So let me classify the building blocks into three categories. The first one being software. So one standard software building block, I'd assume, is an operating system or a command line interface combined with a test executive. Let's assume this scenario involves a Linux-based operating system with a Linux-based command line interface. So that could be a standard building block that spans across an entire category of devices. Right? Another building block could be, you know, for an Android-based device, for instance, it's an Android command line interface that can be built upon, let's say, on a standardized platform like Android Debug Bridge. And some other customers have Windows-based software building blocks. A second major building block is the automation platform, and the automation platform often also includes, it includes duct handling, duct tracking, duct logistics, but it also may include an entire thermal infrastructure that is seamless between, let's say, device to device to device. You get to reuse the same thermal infrastructure that exists. A third piece of this is the electrical infrastructure. And the electrical infrastructure, I mean, something like USB 3.0, Ethernet, SPI, I2C, and some protocol-aware testing. So all of these could also be standard building blocks. So these standardized building blocks really revolve across multiple disciplines of engineering, and we would be glad to talk at depth with anyone who's interested more in understanding the standardized blocks that we've developed over the last several years.
Okay, thank you. One question that came in, will this webinar be available later? Yes, it will be archived and available shortly, and you will receive an email with how to access it, and you can recommend it to your colleagues. And you could just go to www.evaluationengineering.com as well. Okay, and I think we have another question here. Say we have a system and a component in it which needs to be tested. Won't it be more cost effective to know what the parameters and patterns should be for that particular device and then to the component level test? I think this question gets to the difference between functional test and system level test as developing test patterns.
Right. So I think a lot of customers do start with this notion of being able to take a failure at the system level and then somehow being able to translate it into developing a pattern on the ATE. Right. Now, and it's entirely doable. It's certainly possible, but it may not be possible in the time frame that's required for either the process to mature or in the time frame that you've got for ramping up that particular device. For instance, if you've got a scenario in which, let's say, the software just crashes when in the middle of a graphics application, to be able to translate that particular failure from how that software crashes in the middle of a graphics application to developing a vector that would screen it requires a software engineer's help, a firmware engineer's help, and often a DFT engineer's help. So being able to transition across these different industries across these different disciplines within the same company also is often a challenge.
Okay, I think we're coming close to the end here. If we did not get to your question, we will follow up offline, but here's one that seems to be of concern to a lot of people. How can customers afford to add system-level test insertion? Another test insertion could seem to be kind of a hard sell.
The system-level test insertion often pays for itself in terms of return on investment. So there's an outgoing DPPM after the final ATE test over to the customer. Let's assume for a second that this cost of the system-level test is X. But the cost of failure, let's say, is just $10 at the final test level for a given SoC. By the time that SoC moves into, let's say, a laptop, for instance, the cost of that failure goes up to $1,000. And if that failure is actually detected in the field, then it's significantly higher than the cost of the laptop in terms of the failure. So just purely in terms of return on investment, it's really system-level test often pays for itself, especially for complex devices and at shrinking node geometries. Another key level for system-level test is in critical applications such as medical devices or in automotive applications, the cost of a failure or the cost of even 20 or 30 dBPM is so exponential that it pays for itself in terms of having system-level tests to ensure that the quality concerns are met.
Okay, good. Thank you. Our time is up, and as I said, if we didn't get to your question live, we will respond offline. Thanks again to Anil and Karthik, and thanks to everyone for participating.
Thanks a lot, Rick, and again, thanks to Evaluation Engineering and for those that participated.
Thank you.